For our third lesson in this half unit, we're going to talk about piecewise-defined functions. Our goal is to be able to graph piecewise-defined functions given their equations, given the rules, or write the rules of the function of the piecewise-defined function given the graph. So in order to do this, we need to know what a piecewise-defined function is and what the rules are. So basically, when we define a function, we have the equation, we have the graph. There's different ways to represent the relationship between the x's and the y's. Typically, there's a rule, and then we make the graph based on the rule. But a piecewise-defined function is defined in separate pieces over the domain. Instead of like, this is the rule, it's, hey, maybe there's this rule for this part of the graph, but then there's that rule for that other part of the graph. What we're going to do is look at different intervals of the domain, and we're going to define the graph with different equations. All right? So here is an example of what that might look like. Here we have, and I know this looks pretty intense, but the function is going to look like this line, the opposite of x plus 2, for when x is less than or equal to negative 2. Meaning, we would have this graph, but only up to negative 2 with a filled-in circle. But then we also say that the function is going to be 8 minus 1/2 x squared from negative 2, not included, to positive 4, included. So we look at the graph of this whole parabola, which we know how to graph from our last couple class meetings. We'd have an open circle, and we would only graph the parts and pieces that are between these values, greater than negative 2, but less than positive 4. And then for the third part, we have y equals 1/2 x plus 1, but only for the values where x is bigger than 4. So we have an open circle, and we would draw an arrow that way. Essentially, what we want to be able to do is make the graph without the blue dashed craziness, right? We're just going to have the bold parts that I have drawn with my marker. That's how a piecewise-defined function is going to look. Sometimes it's helpful to kind of see it like so. This might not be a continuous graph. It might be where it goes to a point and then it leaps off with a non-included, and then we work from there, et cetera, et cetera. Sometimes you have a filled-in circle there and an open circle there. It just depends on how it works. It will never be filled in and filled in. That's not going to be a thing, because otherwise that would break the rules for functions that we'll continue to learn about and chat about as we move forward. So what we want to be able to do is try our best to graph these functions in pieces. So we're going to try our best to graph these functions in pieces. We've got the line 2x plus 6 for the values that are between negative 6 and negative 2. That includes this, but excludes that. The graph of 2x plus 6 looks like this. And we should be pretty good at graphing lines, either from our Algebra 1 work, or using our grapher calculators, or understanding our parent functions. And so this would be the graph of y equals 2x plus 6. But I only care about the values from x equals negative 6 to x equals negative 2. All right, these kind of vertical lines. All right, so in between these values of x, what have we got? We're going to have a filled-in circle there. We're going to have an open circle there. We are going to connect those dots using a ruler. And that is the picture that we're going to have for this portion of the graph. Then I'm going to use the parabola x squared minus 2 over this part of the domain. Well, x squared minus 2, we learned, is going to look like this. 2, 1, 2, 3, 4. 2, 1, 2, 3, 4. Over 3 up 9. That's 4, 5, 6, 7, 8, 9. And that's what this parabola is going to look like. It's going to be this kind of whole thing here. This is the whole parabola. All right, but I don't care about the whole parabola. I only care from negative 2, filled in circle, up to positive 3. 0, 1, 2, 3. This output right there. Oops, but that's an open circle. So we're going to put an open circle there. Essentially what we're doing is graphing 3 separate functions, but for different intervals of the domain. X is greater than or equal to 3. So at 3, y is going to equal 1, 2, 3, 4. This is a constant function. We will have a line that looks like that. Filled in circle on this part, because this is less than or equal to. Filled in circle, this is going to be like this. This is going to be like this. This is going to be like this. All right, so we kind of know what the end points of those functions are going to look like, or of those steps of the function. This is graphing a piecewise-defined function in its separate pieces. Sometimes you have 2 pieces, sometimes you have 3 pieces, etc. All right? I want for you try this. Don't skip it, try it. You try it, and then we will confirm if you did it right in class. I will check that one. Now, you might need another example. Come see me in seminar, or just look up piecewise-defined functions and see if you can get another explanation. But I'd love to see you in seminar to ask that question. All right, moving on. Writing an equation, or writing the rules based on the graph. Right? This can be a little bit tricky because we have different things happening. And what I want to remind you of is how to write a linear equation. So there's a little bit of a reminder here. There are 2 things. First of all, you need a y equals mx plus b, right? Y equals mx plus b. The m value is found by taking the difference in y's divided by the difference in the x's, right? y2 minus y1 over x2 minus x1. You can also get the equation once you know what the slope is, and if you know one of the points on the line, by using what's called the point-slope form. Y minus y1 is equal to the slope times x minus x1. If we know the slope and we know an x comma y, then we can write y equals mx plus b. Distribute the m, add the y1, and we're good to go. Should take 4 lines of work max. All right? Over here, we've got this graph for the first part, from -2 to, it looks like 1. All right? And so our goal is to figure out what is the equation of this line. There's a couple ways that we can try our best to figure this out. One is we can count the m, and we can acknowledge what the b value is. So if we want to do the first part, so f of x equals, and then we'll have our brackets. We've got 3 pieces, the blue, the red, the green. And for the blue part, this is only defined from -2 to +1. So -2 is less than or equal to x, is less than +1. And the equation there is, again, y equals mx plus b. So we're going to write just the mx plus b part here. You can do all of this work to find it, or you can be investigating here. We go from -10 on the y up to -4. All right, so that's the difference in y's, minus -4. And then our difference in x is we go from -2 to 0. And so you can either count rise over run. It goes up 6 over 2. If it goes up 6 over 2, then we're going to get a slope of 3. Now I know that I did that backwards, so I got negative over negative. Right? I went down 6 back 2, but it's the same as if I go up 6 forward 2. I'm going to find that the n is 3. So I'm going to have 3 times x, and then what's the b value? The b value is -4. There you go. We've got the equation y equals 3x minus 4 for the blue part. But only for -2 is less than or equal to x is less than 1. Then for the red part, we have this line. And now if I'm going to extend this out, we would see that the y-intercept would be at 3. Or I can use the 2 points. If I'm going to find the equation of the line, let me model that for you using this equation. If I'm going to find the equation of the line, I would take the y2 minus the y1 divided by the x2 minus the x1. This is going to be 4 over 4, which is 1. So the slope is going to be 1. And then I can use my y minus y1 equals m times x minus x1. Remember, we got x1, y1. I just used those same values. So y minus 4 is equal to 1 times x minus 1, or y minus 4 equals x minus 1, y equals x plus, what did I say the y-intercept was? At 0, 3. So y equals x plus 3, but only from x is +1 included, and included with x is equal to 5. The green part is just a constant, and this is y equals 8. It's a horizontal line, y equals 8, but only from 5 is less than x, all the way over to x equals what number? All the way till x equals 8, inclusive. And so now we have written the equation for 3 lines over 3 separate portions of the domain, 3 separate intervals of the domain. Again, writing that in kind of that set builder notation of the inequalities there. All right, now if this was going to go on to infinity, we'd have it go 5 is less than x is less than infinity. If it went from -infinity up this direction, if this had an arrow on it, we would have -infinity here to say that, hey, this is going to go on forever. And so we can still use that same notation that we learned about when we were talking domain. I would like for you to draw this picture to the best of your ability. And then I would like for you to try to do this one. All right, this is, I know that this is hard, but by practicing it before you come to class, you will be in so much better shape than in what we're going to do. Give this a shot. Giving it a shot isn't, oh, I didn't know how to do, so I didn't do it. You should be able to do something, all right, some parts of it. So I'd like you to try that. I would like for you to figure out if you can at least identify what are the intervals. Can you find the equation? If you found the equation and it turns out to be wrong, there's no problem there. We're going to go over it in class, and so you'll find out. All right, that's basically it. There is this idea of a step function that is sort of saying like think about shipping rates is kind of this example here. It's like, well, if you want to ship something that weighs 2 pounds or less, it's going to cost you $4. If you want to ship something that weighs over that up to 5 pounds, then you're going to have to spend $5 for it to ship. If you want to send something that's bigger than 5 pounds up to 8 pounds, it's going to cost you $5.50. To mail that thing. And so this is kind of a step function, and it's defined, as you can tell, in pieces. What would it cost to ship a 3.2 pound box? Well, if its weight is about 3.2, it's going to cost you $5. What weight? Which weights would cost $6.50? $6.50. That's this right here. So bigger than 5, but less than or equal to 8. 5 is less than x is less than or equal to 8 pounds. All right, between 5 and 8 lbs. All right, but also including 8. So that's why we have the less than or equal to. Why does the function start with an open circle? You're not shipping something that weighs 0 pounds. All right, you're not shipping something. You're gonna have to write that down yourself. You're not shipping something that weighs 0 pounds. Something weighs something. Everything weighs something. Write the step function as a piecewise defined function. Ooh, this is tough. All right. So we have a lot of steps, 1, 2, 3, 4 different things. And we're going to say that y is equal to $4 for 0 is less than x is less than or equal to 2 pounds. But then it's going to be $5 per pound if it's bigger than 2 but less than 5. And then it's going to cost $6.50 for less than or equal to. For something that is bigger than 5 pounds, but less than or equal to, how much is that? 8 pounds. And then the last part, I don't know if you can see it, it's going to cost you $8.50, and that's going to be for values that are between 8 and up to 12 pounds. So they're saying that they won't ship anything that's bigger than 12 pounds. This is 5 less than x less than or equal to 8. This is 2 less than x less than or equal to 5. And then this is 0 less than x less than or equal to 2. All right, so those give you the different intervals and the different costs for each of those weights of the package. All right, for our last example, we have this step function. And so it's going to be -3 when it's less than 6. So -3 less than 6. We're going to have an open circle going forever. It's going to be 1 from -6 inclusive to -3, open circle. It's going to be 5, 1, 2, 3, 4, 5, from -3 inclusive to 0. And then it's going to be 9 when we have greater than 0. There's your step function. All right, that is the end of the lesson. Hopefully now you can understand how to graph piecewise defined functions and how to write the equations for piecewise defined functions. See me if you have questions.